He knows a lot about the science stuff. Professor Dave explains.
Okay guys, so for today we have a synthesis problem, and we have a target molecule here and we have some allowed starting materials. So what we're saying is that we're starting from benzene and any compounds of 3 carbons or less. So we cannot use any compounds with 4 or more carbons. We have to be using benzene and then other compounds involving 3 carbons or less, and this is going to be our target. So see if you can construct an efficient synthesis of this molecule using the reactions you know. Okay, so let's take a look at this target molecule. Now, as we're recalling our allowed starting conditions, we're immediately going to run into a problem, and that is this. Although that we have 2 fragments here that seem like they might be pretty easy to attach via some friedel-crafts chemistry, we're noticing that this fragment has 4 carbons in it. And so we are not going to be able to attach that fragment as is all at once, because that does not meet our allowed starting material requirements. We are going to have to do something. We're going to have to take that apart some way. So let's utilize a little bit of retrosynthetic analysis. And what can we go back from that is going to dismantle this to some degree? Well, let's look. It's a little bit subtle, but we know that we have a carbonyl here, and we have an alpha-beta degree of unsaturation, right? This is an alpha-beta degree of unsaturation. We have a pi bond that is in the alpha and beta position relative to this carbonyl. And so ideally we can look at that and see that there could be some enolate chemistry that could produce that, because we know of a reaction like, say, an aldol condensation that is going to produce that degree of unsaturation. And if we were to be doing that kind of enolate chemistry, then all the action would have been happening here. And so that means that we could have attached this carbon right here. This carbon could have been attached by enolate chemistry. So for now, let's just go back and say later in the forward direction, we'll make it abundantly clear what we're going to be doing. But let's just say that we can go back to this, right? So we're going to say that we can lop off that carbon going back in time in a retrosynthetic sense. We can get backwards to this. And then now from here, this looks a little bit more reasonable, because we have a couple of fragments that we're thinking we might be able to attach now by friedel-crafts chemistry. And we do indeed have 3 carbon fragments, so we're in a little bit better shape here. Now, we do want to think about the order in which we want to remove them, because that is going to inform the order in which we're going to attach them in the forward direction. And so we look at these guys, and we can see that they have a para relationship, right? These have a para relationship with one another because they're on opposite carbons there on the ring. And this alkyl group is an ortho-para director, right? And this, because of the position of that carbonyl, this is actually a meta-director. And so we're trying to think, which one of these are we going to remove first? Well, we have to remove the one whereby we are leaving the other that would direct the incoming one to its place. Because they're para to one another, and this is an ortho-para director, then this group must have already been present on the ring in order to direct this group to its place. So if we're going to go back a little bit, we're going to see that probably we came from this, right? This has to be in place first in order to allow for this group to then attach to the correct position. And then from there, we'll probably be able to figure out some chemistry to get all the way back to benzene. And so if we can get all the way back to benzene, then we're good, because we've said that we can start from benzene. So let's see how we're going to do this in the forward direction. We have benzene, right? Right, so now that we've completed our retrosynthetic analysis, we now need to go in the forward direction and say what reagents we're going to use. We have to prove that this was valid by then showing very rigorously what we're going to do in the forward direction. So if we're trying to go this way, we want to attach this alkyl fragment. And so anytime we're attaching an alkyl fragment to benzene, we're thinking we're going to probably do friedel-crafts alkylation. But there is one problem here, and if we saw in another tutorial when we talked about Clemmensen reduction, the problem is this. If we try to do this, let's say we tried to do this, right? If we wanted to do that, what would be the problem? Well, the intermediate, we would have an intermediate that looks like this, right? Because after this chlorine interacts with that aluminum, and then that carbon-chlorine bond severs, we're going to be left with a carbocation intermediate. That is what benzene interacts with, right? That's the more reactive intermediate. And if we have a carbocation that can rearrange, it will, right? So this would immediately rearrange to give the secondary carbocation by a hydride shift. And so then we'd have benzene interacting with this instead, and we would not be getting this linear fragment. So that's a problem. We cannot use friedel-crafts alkylation to do this. But there is a solution. What if we do friedel-crafts acylation instead? So once again, let's use a 3-carbon fragment. That is allowed. Remember, we can use anything of 3 carbons or less. And so we've got this 3-carbon friedel-crafts acylation reagent. And let's go ahead and do an acylation. And you know what, let me move it over just to keep everything in the same position as here, just to alleviate any confusion. So we know that we are going to be attaching all of this onto the ring, right? So there's our friedel-crafts acylation product. And the reason that this is useful is that now we can go ahead and do Clemmensen reduction. So that is amalgamated zinc, right, complex with mercury in hydrochloric acid, and that is going to allow us to go to the alkyl. Let me do that one more time. That is going to allow us to go to the alkyl fragment. Right, so this is a reduction. We're going to get rid of this carbonyl, right? We're going to be able to lose that carbonyl via Clemmensen reduction. And so this is our 2-step process that represents this one move in our retrosynthetic analysis. To go from here to here, we had to do a 2-step reaction because if we did friedel-crafts alkylation, we would have gotten an isopropyl group right there instead, and that's not what we want. This is our target molecule. We can't change that at all. So we did our friedel-crafts acylation followed by Clemmensen reduction, and we're here. So now on this, we're here. And we're still trying to go this way to get back to the target. So we're here, and we said that we could have done some friedel-crafts chemistry to get this. And that's great because this is an orthopara director. So what if we did just the same friedel-crafts chemistry again? Let's do this. So this is the same friedel-crafts acylation that we did initially. And since this is an orthopara director, and the fact that there is some steric hindrance associated with both this fragment and this incoming molecule, you may get some competing ortho substitution, but predominantly we're going to go para. And once again, the reason there is sterics. So we will, the para substitution will probably predominate in solution. And so now we're here, and what can we do from here? Well, we said that maybe we're going to be doing some enolate chemistry here, right? So how can we do some enolate chemistry? We've got one more carbon to get on there, and we can do enolate chemistry where an enolate is attacking a 1-carbon aldehyde. That would be formaldehyde, right? So why don't we just go ahead and do that? We can say that we're going to, let me make that a little smaller so I have room. Let's say that we are going to do, well, we need some strong base, right? We need that, and we need formaldehyde. And if we do that, and we'll just show both steps right here, we are going to go first to this, right? This will be the new bond right there. That would be our aldol addition product, right? So that's what would happen if we enolized right here and then this carbon attacked formaldehyde. We would be attaching one carbon right there, and then that would continue, especially with heat. We would just go ahead and enolize again and then kick that off, and we would just get our aldol condensation product. So this is our aldol condensation product. And so again, you can go back to the aldol condensation tutorial to check out that mechanism in a little more detail, but this is how we're going to tack on that last carbon. And so just once again to take a look at this, we said that we needed compounds of 3 carbons or less, and that is what dictated this, this sequence here. We wanted to remove 1 carbon because this had 4, and we went back to here. Notice that this is ortho-para directing, this is meta-directing with a para relationship. So this had to come on first, meaning we remove that, we're here, this goes back to benzene. So that was our logic during the retrosynthetic analysis. Now in the forward direction, in order to go from here to here, we saw that we were going to do friedel-crafts acylation followed by Clemmensen reduction to get to here. And then to go from here to here, that was simply the same friedel-crafts acylation again to get to here. And now we were almost done, right, because we're here. We just have one more thing to do. We needed to tack on this 1 additional carbon, and ideally at the beginning, the thing that we hopefully saw was that this is an alpha-beta degree of unsaturation. As an alpha-beta relationship to this carbonyl, that ideally tipped us off to the possibility of some enolate chemistry, specifically aldol condensation. And then we saw that we could attach a one carbon fragment there by enolizing here and reacting with formaldehyde to get our aldol addition product. This 1 carbon there was the formaldehyde carbon, and then this would inevitably continue to give our aldol condensation product, which is the target molecule that we were desiring. Thanks for watching, guys. Subscribe to my channel for more tutorials. Support me on Patreon so I can keep making content. And as always, feel free to email me, ProfessorDaveExplains@gmail.com.